Hello and welcome. In this video, we'll help you kickstart your journey with Slurm. Whether you're running Slurm on Google Cloud, another cloud provider, or even a self-managed system, these concepts will apply to you. Today, we'll demonstrate using a Google Cloud environment, which I've already set up for us. If you need guidance on setting up your environment quickly and easily on Google Cloud, check the video description for a related tutorial. We've also included the YAML blueprint file we used to spin up this cluster so you can follow along step by step. As a quick introduction for those who might be new to it, Slurm is a workload management system that's particularly useful for AI machine learning and high-performance computing workloads. Ever wondered how large-scale compute jobs are managed efficiently? That's where Slurm comes into play. In our Google Cloud setup, we're leveraging a few managed services. Specifically, we're using Compute Engine, or GCE, for our Slurm nodes. We're also using FileStore for our file storage, providing us with the convenient file system interface for our jobs. Additionally, we're using cloud storage for object storage. This combination gives us a robust ecosystem to run our workloads smoothly. Essentially, our ecosystem comprises compute resources, storage solutions, and backend networking systems. Let's log into our login node here using Google Cloud's SSH in-browser feature. This is where the fun begins. We'll start experimenting with Slurm commands and discuss some important concepts. For example, running the sinfo command gives us a wealth of information about partitions and nodes. Curious about what's under the hood? Let's find out. This system has two debug nodes running at all times in the debug partition alongside our controller VM and login VM. If needed, we can scale beyond this and expand the node set within this partition. Flexibility is one of the strengths of this setup. We also have an H3 partition utilizing Google Cloud's H3 nodes. These are high-performance, though pricey, VMs, boasting 88 virtual CPU cores and hundreds of gigabytes of RAM. Need some serious computing power? These nodes have you covered. Finally, we have a compute partition that auto-scales from 0. Unlike the debug partition, this partition is exclusive. It runs one job, spins up, and then deprovisions the nodes, unlike our always running debug partition. This helps in optimizing resource utilization and cost. The little dashes you see indicate that the nodes are in power save mode and will be provisioned on demand, so we don't need to have dozens of nodes running all the time. Note that our home directory is actually mounted to our file store system provisioned with this cluster. This NFS share provides about a terabyte of space, plenty of room to do some development. Now let's walk through a simple Hello World example job. We'll write a bash script and run it as a job using the sbatch command. In the script, we can specify our batch job configurations. Ready to see Slurm in action? Let's get started. First, at the top of our script, we'll specify that this is a bash script. We'll call this job hello and specify which partition we want to run on, specifically the debug partition in our case. We'll use a single node for this simple example and specify the number of tasks equal to 1. You may be wondering about the difference between number of nodes and number of tasks. The number of nodes refers to separate VM instances. For example, if we wanted to run over 2 VMs, we would change this number to 2. The number of tasks connects this job to specific CPU cores, which is important when running many jobs over multiple clusters. Essentially, we're requesting one process for this job via this argument. We'll also specify where we want our output to go. For our simple Hello World example, we'll just echo our command, let it sleep for a bit to simulate a running job, and then print a completion statement. To ensure the script is executable, we'll grant execute permissions and then submit it using the sbatch command. We can check the job status by running the sq command. As you can see, it's running on the first node. This job should take about 30 seconds to run since we don't need to wait for dynamic VM provisioning. All right, there's nothing left in the queue, so our job must have completed successfully. Let's check the output to confirm. Just as expected, we have the host name we ran on the first node in our node set, and then the completed message. But what if we want to run commands interactively? We can do that using the srun command. Let's run this on the debug partition and initiate a bash shell. Now, as you can see, we're on the first node. This method allows us to interactively explore the node, a useful feature for debugging and early development work. To reinforce the concept of using different partitions, essentially different job queues often backed by different nodes, let's create another job. We'll call this one compute because we'll run it on the compute partition. We'll start similarly to the last job by specifying some arguments, most importantly that we're running on the compute partition, which will be dynamically provisioned for us. We'll use 2 nodes and allow up to 4 processes on each node, giving us a total of 8 processes. We'll also specify a time limit and an output file. In this instance, we'll keep things simple by running some print commands and checking the host names. Specifically, we'll use the command srun hostname to run the hostname command on the nodes. Now that everything looks good, let's submit it using sbatch as we did before. If we check the queue, we see it's creating a couple of nodes dynamically. However, if we refresh a few times and don't see those nodes coming up, it's time to investigate and ensure everything's working correctly. In this case, it's attempting to spin up 4 nodes because the first 2 didn't work and are showing as down. We can use the scontrol command to see what's happening with these nodes. It turns out it's rejecting the number of CPUs we're trying to use in this node set configuration. So what's going on here? Let's dig into our setup to find out. Unlike the debug node set where we explicitly specify a machine type in the compute node set, we're using the default configuration. Let's check the module for this node set in the cluster toolkit to see which VMs it's trying to use. Searching for the machine type reveals it's trying to use 60 core machines. We can't spin up 2 of these simultaneously because it surpasses our quota. Rather than applying for a quota increase right now, let's adjust our script to use just 1 node. Once the failed dynamic provisioning of the compute node set is finished, we can resubmit our job. Now, as the allocation drops, we can see that we're only allocating 1 node. Refreshing the page, we confirm that our compute node is indeed running the job. After a successful VM provision and a runtime of about 60 seconds, the job should complete. And right on schedule, our job finishes, and we can check our output. We ran that job on node 6 across 4 different processes, as specified with the parameter n-tasks per node equals 4. However, note that only the parent process on the node had the printouts for job start and end time. Now let's take this a step further and modify our setup to perform a multi-node run on 2 debug nodes. These jobs should be quick to run because we already have those nodes running at all times. Interestingly, while nodes 0 and 1 are continuously running, our compute node has actually deleted itself after accomplishing its task. It was dynamically provisioned. Once again, at the 60-second mark, we're all set, and now we should have an output where we ran on both nodes separately. For just the parent process, we have these prints. We could, of course, continue experimenting with different combinations of partitions, node sets, multiple nodes, and number of tasks, but I think you get the idea. Let's run a quick command to see all the jobs we've been running so far, including their current state. For example, you might notice we had to cancel the compute job due to project quotas and had a failed job because we didn't have enough CPUs on our debug partition based on our job specification. To dive deeper into the job details, we can use the scontrol show job command to see specifics like where the output was and plenty of timing details. Additionally, we can use the sf command to look at the efficiency of that job, particularly in terms of CPU, memory, and GPU utilization. This is especially beneficial when running accelerated workloads or, more broadly, for high-performance computing work. Now, let's explore another powerful concept in job management, job arrays. We'll create a script here for us to run. Crucially, we're adding an array argument from 1 through 10, which means we'll run 10 separate tasks, each having its own unique ID. As you can see, this has created 10 separate jobs. These are likely to be run on different nodes and will auto-scale our debug cluster as needed to accommodate that. Some of these jobs took off pretty fast because they used the pre-provisioned nodes. A few other VMs have spun up as well, so once the jobs are assigned and start to run, they should finish relatively quickly. Once we reach the state where we're executing the job, it should just take about 10 seconds. And we're done. If we look at our array outputs, we have all 10 of them. Let's just look at the first task, which ran on the first node. It printed exactly as we'd expect. To wrap things up, let's look at another powerful capability, job dependencies. Let's copy our Hello World task and call it dependencies.sh. We'll set the output of our dependencies job and save that as job 1. Then we can specify a dependency and state that we want to run job 1 before starting this one. This job is going to take about 30 seconds, and now we have that dependent run. If we double check here, we see indeed that we are waiting for 30 seconds before the script runs. The outputs are all as expected. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comments section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.